So, did you go to the other session that they had? I think it was yesterday where they talked about recursion, or maybe 2 days ago. Can't remember.
No, I didn't actually.
You didn't go? Okay.
I was just added to the group meeting, so I wasn't didn't
Okay.
have anything else.
That is totally fine. There is one algorithm we'll talk today that uses recursion, but we'll take it pretty slow on that one, or like we can talk about that one later. If since recursion is kind of like a big part of it, but we'll go.
Right.
Yeah, but we'll go through most of the sorting stuff, and you'll find out it's really not that bad. So I'm sure at least to the context in the test. So basically in the test, if you check out the kind of material that we have on the ebook, basically what you need to know is like they won't ask you to code it from scratch, but you'll have to know like what exactly searching is, what sorting is, and how do some of the comments, how do certain algorithms look in code. So if they show you code, you should be able to tell, oh, it's this kind of sorting or it's this kind of sorting.
Okay.
Yeah. Um, and the other thing they might ask you, this I'm not sure. I asked my team. They didn't clarify with me, but the other thing you might need to know is like how do some sortings, like if some of them are faster than others, and I'll talk about what faster means a little bit. But yeah, that's kind of like the other things you need to know. You don't need to worry about actually writing the code for that. So yeah.
Okay.
So what?
And recursion is basically when you call a method within the method.
Yeah, that's essentially what it is. It really, yeah, the concept is like it makes sense, but seeing the
Hmm.
actual code and tracing the problems, that is a little bit more difficult. It takes some practice, but we can actually go through that instead of like going through merge sort, which is what uses recursion. But uh, but yeah, that is what it is basically.
Okay.
Yeah. So what do you know about searching and sorting?
Huh?
I said, what do you know about searching and sorting, if anything?
Um, we haven't gotten to this yet,
You haven't
so
gotten to.
I
Okay.
nothing in searching and sorting.
Okay, but are you good on arrays? Like, do you feel pretty comfortable with arrays?
Yes.
Okay, great. So yeah, we'll be talking about searching and sorting in the context of arrays today. Though they have a lot more uses. At least searching does. But yeah,
Uh-huh.
today we'll be talking about arrays, and I think that's the only thing you have to worry about for your tests. But yeah, both of these words they mean basically what they sound like they mean. So searching refers to going through like an array and finding a specific value that you want to find. So say that could be like if you want to find the smallest value, if you want to find the biggest value in the array, or maybe you want to find like just the 7 in an array or the 10 in an array of integers, something like that. So searching is just finding a value you want in some data structure. In this case, arrays. Um, and so the two kinds of searching that you'll have to know for the test, at least conceptually and kind of like also on your code, is sequential and binary search, right?
Right.
And yeah, and the descriptions are here. They're pretty straightforward, but basically sequential search is, I'm sure you've done that before. So you know how like when you do, let's see, let's just check sequential search. So I'm sure this code is going to seem really familiar to you right here. So yeah, you
Okay.
know how when you start at the beginning of an array and they want you to find a certain value in the array, you start at the first one, and then you go up till the end until you find that element, right? I'm
Right.
Okay, cool. So that's basically what sequential search means. It means you go one by one from beginning to end until you find the thing you're looking for. It's really straightforward. The problem with that is like, can you think of some like possible problems with this kind of searching?
It could take a long time.
Yeah, exactly. That's a great answer. Yeah, it could take a very long time, and uh, like in the case of like it's the what you're trying to find is in the end of the in the end of the array, or there's even a worst case. If you can think, you think what might be the actual worst case?
Um, it doesn't run.
I'm sorry.
Right? Like it won't run for some reason.
Yeah. Like how? What's the worst possible case in which this will perform?
I'm not sure.
Okay. Well, one good example that you mentioned was like, or like that we talked about was when it's the last element in the array, right? Because when it's the last
Mhm.
element in the array, you're going one by one, and to get to the end, it's going to take you a while. But if the element isn't even in the array, so say they ask you to find a number in a list of numbers, but that number isn't in that list, then you're gonna have to literally search everything, including the last one, and then you like it'll take longer, right?
Right.
Yeah. So yeah, I think the reason I asked that is because sometimes in the test they'll ask you to think about like when is this gonna be really bad, when is this gonna be really good, and so it's good to think about these algorithms in the context of like when it works best, when it works worse, you know?
Right.
Cool. So that's sequential searching, really straightforward, like I said. The other one that's a little bit more interesting is binary search, right? And so a
Mhm.
very key thing to note here that's why it's bolded is that binary search is only to be used when the array has already been sorted. So you can't use this on a normal random array. You can only use it when the array has already been sorted somehow. And they'll usually tell you if the array has been sorted or like maybe like they'll ask you to like or maybe it'll be sorted using some sort of sorting algorithm, right? But the important thing about
Right.
binary search is yeah, you can only use that. And the way binary search works is let's see. Actually, oh yeah, I wanted to point you to a few resources that were really useful for when I was learning these things. So these are a couple of websites. The first one is Visual Algo, and basically what this shows you is a bunch of like visualizations of different algorithms that are pretty pretty common in computer science, and you may have to implement them someday, but in general this is really good to just know how they work, like see them work. I don't think they have binary search. Yeah, they don't have binary search, but I'll show you some sorting ones after that were really cool and really useful to me. um, yeah. But the basic way that binary search works is that you have an array, and then you start at the middle. And I really want to get a visualization for this. Let me see if I can find one. I'm sure there's one on like Wikipedia. Let's try binary search. Okay, here's a good one. Okay, so right. So the basic premise of binary search and why it's faster than sequential search in the case of sorted algorithms is that you're always going to be cutting what you're looking through in half, right? So initially you start in the middle of the array, right? Which is
Mhm.
in this case is 14. And then you look at that, and then say you're trying to find, in this case I think they're trying to find 7, right? Right. So you're trying to, or is it 7? Yeah, 7. Yeah. So you're trying to find 7, right? So you start at 14 and you check, is 14 greater than 7 or is 14 smaller than 7, right?
Right.
Yeah. And in this case, 14 is bigger, right? So what happens is that everything to the right of 14, from 18 to 71, it gets cut up entirely, right? So all that
Mhm.
disappears, and you don't have to worry about searching that or anything, because you know that whatever you're searching for is smaller than 14, and because it's already sorted, it's not going to be here. Make sense?
Yes.
Great, great, right? And then you just keep repeating that basic premise over and over, right? So now you have from 1 to 14. I'm sorry, 1 to 13, and then you're going to go to the half of that, right? Which is, I guess, 6. Yeah, which is 6, right? So you look at 6 and you say, oh, 6. 6 is actually smaller than 7. So you know that everything over here is not important now, including 6, right? So now you cut all
Right.
this up, and now you only have 8 and 7, right? And then the
Mhm.
middle of that, I'm sorry, you have 7, 8, and 10. And then the middle of that is 8. And of course, 8 is bigger, so it's to the left. And then because at this point the only smaller thing is 7, uh, you found what you wanted. Yeah.
Okay.
So it's pretty straightforward. You're basically, the important thing to know here is that you're cutting things half and half every single time. You're searching through half the things you should every time. So if at first it was 10 things, then you need to only search through 5. and then only through 2 or 3 depending on how you round. But yeah, you're cutting it down in half every time.
Right.
Mm-hmm. Yep. And here's some code. Let's see. Yeah, you should be able to recognize this, but okay. So let's get right. Okay, so can you tell why we do from while left less than or equal to right?
It's basically like reading from like left to right.
Mm,
So if there's more to the right, then they would keep going. If not, then it would stop its loop.
right, right. So yeah, you're exactly right. Right. So we do that, and then yeah, first thing we talked about. So you want to find the middle, right? And that's why it's important to keep track of these left and middle and right values because that middle will continue changing as you keep cutting parts of the array up.
Right.
Mm-hmm. Okay. Target less than. Okay, and here you can tell this is the logic, right? Where we cut up, where we decide what part of the array to cut, right?
Right.
Okay. So can you tell me why we do right equal to middle less than 1 and left equal to middle plus 1 instead of just doing right equals to middle?
Um, because you're checking the numbers around the middle rather than the middle itself.
Right, right. So you're saying if I were to get 14 initially, right?
Right.
You're saying I don't care about 14 itself. I only care about what's to the left of it.
Right.
Okay, yeah, that's exactly right. Because when you check it, you initially compare that value to what you want to find. So obviously, if you compared it to that one, you know that that one is also like not going to be what you want, or it could be. You know, 7 was here, but yeah, that's good. And then let's see. I think that's pretty much it. It's a pretty simple algorithm. Yep. And
Okay.
then terminator one. What is it? Return negative one. Oh yeah, I think this is in the case or like you don't have an array or something. Yeah, that's pretty much it. Yeah. So yeah, this is a pretty straightforward algorithm, and yeah. See, as you're probably gonna notice a trend that happens here. When that happens in like the APCS review book is that a lot of the questions are like, what causes this to be really fast or what causes this to be really slow? You know. So yeah,
Okay.
just keep that in mind as you like learn these things. Let's just go through these ones. I think these are pretty simple, but I think I might have actually already answered them because I was like looking through this before starting the webinar. But I guess you can explain to me why. So you know why the shortest execution of binary search will be when the value's in the middle of the array.
Because it cuts it in half and it looks at the number in the middle and everything to the left or to the right. And if it's not the number in the middle, or if the number in the middle is less than or equal to or even greater than, it's going to ignore. If it's greater than, then it's going to ignore everything that's less than that number. But if it's less than, then it's going to ignore everything greater than the number.
What if it's equal to?
If it's equal to, then you just have your number already.
You just return that.
Right.
Okay, great. Yeah, that's exactly what happens. So that would be like the best case scenario for you. All right, and then yeah, we talk. I guess this one I can't really ask you, but yeah, just keep in mind this is the most important rule about binary search the array must be in order. Everything else is like duplicate values don't matter. Yeah, that's pretty much it.
Okay.
And then yeah, I can't really. Yeah, this is one thing I've always, the one thing that we should probably fix about the ebook. For some reason, if you answer like the question and then like come back to it after, the answer stays like there. So like sometimes I'll like do that and then do the webinars and I always forget about that. But you think you're pretty straight with binary search?
Yes.
Great. Yeah, so I mean you can probably tell binary search and like sequential search, really simple stuff. I'm sure you'll get it like super easy in the test. So yeah. Right. Sorting is a little bit harder, but there's the good thing about sorting is there's actually a lot of good like resources and visualizations that will just kind of like show it to you in fun ways that's easier to learn rather than just looking at some numbers in a list, which is kind of like abstract. So yeah, that helped me out a lot. It's funny, this class actually, this video she posted here, I actually used when I took the my first CS course in college. So it's just a really good video. But basically, what this video does and what Visual Algo does is that it'll walk you through. It'll have basically some data, and you can tell what the value is, and it will sort it for you, and then tell you what happens at every single step. So these are really helpful, right?
Right.
And yeah, but basically sorting is, I think I briefly talked about it, but basically sorting is when you want to get a list in ordering from least greatest to the greatest, right? So if you have a list of numbers, you'd want to get it from the smallest to the greatest, and you could also do this with like strings or something. Like say if you want to do alphabetical order, but that takes a little bit more doing, to get like to be able to tell what that ordering is, right? So we're just going to talk about in the context of integers right now, right? And so there's a bunch of sorting algorithms. You can see right here there's a bunch of them, but the only ones that you need to know for the test, and this is pretty important, is selection sort, insertion sort, and merge sort. So you can learn about the other ones if you want. In particular, if you're having trouble understanding these, I recommend you look at bubble sort because it is the simplest of all of them. So, and it'll just help you grasp the concept of sorting if you're having trouble with that. But yeah, those are the only three you need to worry about for the test.
Okay.
Yeah, so let's start with selection sort. And yeah, selection sort and insertion sort are pretty straightforward. Merge sort is the kind of complicated one, but yeah, let's go through these ones. So basically, yeah, here we go. Actually, I think it might be useful, okay, to have the pseudocode here. Okay, great. So, right. So what have, okay. Is this what happened? Let me just make sure. I want to make sure I'm giving you the right information. And then it puts it first spot. Okay, great. Yeah. So basically what happens in selection sort is that kind of similar to the way you did sequential search, you're going to be searching through an array of numbers until you find the smallest value, right? So it starts at 20, right? And because it doesn't have anything else there, the initial smallest value is 20, right? But then immediately as you go to the next value, which is okay, see, this is another great thing you can do here. You can make it slower in case you're having trouble following. So it's just really customizable and really like nice. So I really recommend this site. But yeah, so yeah, you start with 20, and 20 is your smallest value, right? And you keep track of the index of that number, right? Because you want to move whatever is smallest to the first spot in the array, right? So you come up to 20, and then you see 15, and you're like, oh, 15 is smaller, right? So now 15 is your smallest index, right? But then we look at 10, and then 10 is your smallest value, right? So you keep changing that as you keep finding smaller things, and then now it'll keep looking through the other things, and the other ones are not smaller, so it's just like, okay, keep going, keep going. Oh, and then 8 is smaller. Let's keep that as our smallest index, and it keeps doing this until it gets to the end of the array. Yeah, and now makes 4 our smallest value. And then you'll notice, even though there's repeats, you don't have to change the smallest value because you already have one that's equal. So you just leave the smallest value being 4. And then you keep searching until you get to the end of the array. And then you move whatever your smallest value was to the beginning of the array, right? And then you just do that for and then now you know that this one is sorted. And then you just do that for every single other space in the array. I'll just put it on real fast now so that you'll see like, yeah. Then you find the other smallest values and you move it here, yeah?
Right.
Yeah, and just keep doing that until you get to the end where you know the biggest one is already going to be at the end. Make sense, kind of? Cool, cool. Right, so let's look at some code now that we saw the pretty thing. I do recommend this video too, though I prefer Visual Algo, but whatever helps you understand it better. Right? So actually, now that you saw the visualization, hopefully you didn't see that code, and now you saw the visualization, what kind of things do you think the code for this would have?
A for loop, or maybe even a nested for loop.
Okay, what do you think it would have a nested for loop?
So that first it would go through every item, and then it would hold on to whichever item is considered the lowest value until it finds another item that has a lower value than that one. But then you need another for loop to set that lowest item as the next. When you're setting it in order, you need another for loop to set the lowest valued item to the first item, reset, to basically keep going through the numbers until you basically have it in numerical order.
Yep. Yeah, that's perfectly right. Yeah, you make a lot of sense. I think you understand it pretty well. But yeah, that's exactly how it works. So you start with a for loop, just like our sequential search. You start with a for loop, and you start, at the first value, right? Which in this case is the min index, because you naturally assign it to the min index because you haven't compared it to anything else up to this point, right? So it's like you said, so basically the first for loop, what it does is that it goes through everything and it puts it and it finds what belongs in that spot, right? So it'll do this for like every spot and put the correct thing every time with every iteration of this for loop, right? Whereas this one, it's like you said, this one is for comparing, right? So you compare whatever is in that spot that you're searching for in the other for loop to everything else in the array, right? Yep, and that's exactly what happens. And you keep changing the min index as you find smaller values, and then you just replace it with that. Yeah, it's important. I'm sure we've done this other times, but this is something that I forgot to do a bunch when I was starting the program. Create a temporary value so that you don't lose whatever. So if you're trying to exchange two things which are in two different spots, you don't want to just directly assign like this first. Because if you do this, you'll lose whatever was in the original elements J, and you don't want to lose that because you will have to move it somewhere else. So that's why you need to create a temp. That's just, I'm sure you already knew that, but I just want to clarify that in case.
Can you declare the temporary value outside of the for loop?
Can you declare the temporary value outside of the for loop? Why would you want to do that though?
You're right. Okay.
No, I mean it's fine. It's fine if it's wrong, but just like kind of like, what's your train of thought? Why would you want to do that?
Maybe you would do that if you need to retrieve it outside of the for loop.
Okay, I see what you're saying. So if you want to use it outside of the context of this like for loop, you're saying I should put it like, for example, like here, right? In temp. Okay. Yeah. So I see what you're saying, and it will make sense. However, the reason why we leave it here, you might have seen this already, but the reason why that happened, actually, can you see why we leave it in here? Why we need to leave it in there in the for loop?
Yeah, so that it keeps changing.
Yeah, exactly. So every time you get to a new spot, you want to keep it there because you want to keep exchanging like two different numbers, and so you need to make sure that like those numbers are going to change with every single iteration of the for loop. So you need to make sure you're not exchanging one of the ones that's already in the right place.
Okay.
Yep. So it's exactly right. And then they just have you can run this code here. So later, if you want to change it to yourself, maybe test some different examples. So can you think of like when this would work really well or really fast, and when it will be really slow?
It would probably work the fastest when there's fewer values.
I'm sorry, when there's fewer values?
Yes.
Okay, that's one. I mean, that's very true. It will work faster. But can you think about like when it would work faster in terms of the ordering of the elements in the array? Because I think in general it'll always work faster if it's smaller. So I don't think they'll ask you that. They usually ask you like in terms of like how things are ordered inside the array.
So if it was sorted in the ascending order?
Okay, let's find out. And what do you think? What do you think that's incorrect? Possibly. Like, what do you think it would make it fast?
If it's already in an ascending order, then you really wouldn't need to put it in another order.
Yeah, you're right. But see, here's the thing: if it's it's not going to be that much faster. It's not going to be faster if you are in ascending order because it's like, okay, so the first value is the smallest, right? But I'm sorry. So remember how we mentioned that selection? It'll still go through everything. It's not like it never finds the smallest thing and then stops. You know, it'll go through everything to make sure that it has found the smallest thing. So even though it's already having the smallest thing, let's check.
Right. So it'll always take the same amount of time, no matter.
Exactly.
What the order is.
Exactly.
Okay.
It's always going to go through everything. Yeah. It's always going to do everything because it's going to go through the entire list because it thinks, oh, I need to check the entire list to make sure I didn't like accidentally miss something that's smaller and belongs in the first spots, you know? So that's why it does that. Yeah. Which is nice because that means it's less likely to screw up, but that means it'll take longer, you know? And that's some things that you'll see in computer science you have to consider a lot, you know? Do I want it to always work or do I want it to be fast but sometimes screw up, you know? That's things you have to consider. All right, and then let's see that. Let's look at this question. This matrix is sort numbers in past array into the same array. It does not. Yeah, can you tell what could be wrong in here?
For line 1, why is line 1?
Why is line 1 what?
Elements.length -1, while line 3 is elements.length. Does that matter? Really, in this case?
Yes, it does matter because remember how this works, right? So you go through the entire list and you go through the entire list, right? And you like let's just check what happens when you get to like the end of it, right? So as you keep sorting it, you know, you keep searching the rest of it, right? But as you get to the last one, you already know that the one to the right is already sorted. So you don't need to search for that one. So that's why you stop at elements I -1 instead of going through the whole thing.
Okay.
Right. So once we get to 44, we already know that 44 is like this one is bigger, you know. So that's why here. Okay, that's why here you see it's I -1. Whereas here, you know, we want to compare to every single thing. So that's why you need to go through the entire list, right?
Right.
Yeah. So that's why that happens. So that I don't think that's a problem here.
Okay. is there something wrong with line 3?
Line 3?
Yes.
Let's see.
I feel like it's one of the for loops.
Oh yeah, you're right. Oh, I'm so dumb. Yeah, actually, I guess I misunderstood. Right. I should have caught this. Right. So yeah. So I guess the reason why you said that. So what do you think this one is like? Okay. Next plus
So is it the elements.link?
No. That's I'm sorry. Yeah, the elements on link. Yeah, that's exactly the problem.
Okay.
Actually, wait, no. No, that's not the problem. I knew though. I knew that stuff. So the problem is here that we start at 0, right? So
Right.
so basically you'd be comparing. So like you shouldn't be starting at 0. Like say if we're here. Oh, I'm sorry, I keep getting lost. Okay, so what's going on is that here, right, we start at the first point of the array, right? Because we want to sort everything starting from beginning to end. But here, we don't want to start at the beginning of the array, right? Because this inner loop, okay, so this outer loop is going to run for every single thing, right? And so that means the inner loop is going to run for every single element, right? So that means that once you get to 10, you're going to be checking whatever is here, you know? And you don't want to, you don't want to be doing that because you know that part is already sorted by that point. So whatever this is should be whatever the outer loop index is plus 1. So say if like right now we're trying to find so yeah.
Okay, I understand. I understand.
Yeah. Exactly. If we're trying to check like 20, we don't want to start at 20. We want to start at 15 and then check all those guys. If we want to check 15, we want to start at 10, not at 20, you know?
Right.
Yeah. So that was the problem there. The elements length is not a problem. Think you mostly got that?
Yes. I think I have that.
All right, awesome. Yeah. And yeah, if you ever have any problems that I really recommend these websites, they're good. And another thing that I'm not sure you need to know this for the test, but it could be useful. So yeah, this website is called bigocheatsheet.com, and it basically tells you what these words mean. Is like how. Don't worry so much about the symbols. Worry about the worry about the colors. So red means it's not very efficient. So you can tell here, oh, selection sort is not very efficient because it's always red, right? But insertion sort and bubble sort can sometimes be efficient, you know, or a little bit more efficient because it's yellow. Yeah, so that's just if you ever want to tell which ones are better. In like most cases, like this is just a really quick tool you can look up to see that if you don't want to like sort through paragraphs and stuff. Right? So let's go to insertion sort, and then I think we can leave it merge sort for another day. After you've learned like recursion, we can go through that. But this is most of the stuff you need for the test, so I think you should be fine. So let's go to insertion sort and insertion. Insert index 1. Okay, so the thing about insertion sort is that you're gonna have like a section of the array that you say is already sorted, right? And then you're gonna keep comparing things to that section that is already sorted. So you're gonna keep going back and forth and sorting things. So yeah, look what happens here, right? So we start at so we start at 3, and then we go to 44, right? because we say 3 is already sorted, right? And then we check those two, and then we add. So when it's gold, that means it's already sorted. So right now here we believe that 3 and 44 are already sorted together, which they are. Imagine like 3 and 44 were their own little array, and that would be sorted, right?
Right.
Right. So then we do that, and then we compare the next value to that little array that is sorted that we created, right? And then you say, oh, 34, 38, 38 goes in between those two, right?
Right.
And then you see we have another kind of like little array that is already sorted, right? So this isn't sorted in the grand scheme of things, but it's sorted with these three values, right? So that's kind of the important thing here. And you just keep comparing one value to that little sorted array until eventually that little sorted array becomes the whole array.
Right. So in this kind of sorting, if the values already happen to be in an ascending order, would it still execution? Well, execute.
Yes, it would, but it would be a lot faster because you don't need to move anything.
Okay.
Yeah. So you basically, if it was already in sorted order, we can actually, that's one of the cool things about the site. We can actually check that. So we can do sorted in increasing order, right? And so you can see how it looks sorted, and then look how fast it's gonna go in this case. So it checks 3, 7, 3 and 3, it's already good. 3 and 8, it's already good. Yeah, so yeah, it'll be a lot faster because it doesn't need to move anything. So in a lot of cases, so in the case of this algorithm, it will be instantly fast because it doesn't need to move anything. You know, that's what make your algorithm go slower in sorting, moving things around. But in this case, you don't need to do that, so it'll be instant time, right? However, can you think of what happens in the opposite case, in the case that it's in descending order?
It would probably go slower.
But how slower?
A lot slower?
Yeah. I guess what I was going for is that, so in the way that when it's in increasing order, it goes the fastest that it can. When it's in decreasing order, it's going to go the slowest that it can. That is the worst case, right? So that's another, if you'll notice here, just really briefly talk about this. So when we think about sorting algorithms, we think about them in the best case, the average case, and then the worst case, right? So the best case for insertion sort that we talked about was, when it's in increasing order because it doesn't need to move anything. The average case is like when everything's random, and in which case it's going to be, it's going to be normal. You saw how it was. It's going to perform how it normally performs, right? And then the worst case is going to be like, in this case, decreasing order, right? So because it's going to have to, we can just check this real quick. It's going to have to literally, oh God, sorted, decreasing, sorted. Yeah, it's going to have to move everything like that through everything. So like if I go to 1, it's going to have to move through literally every one of these steps. And it's going to have to compare a lot of times in order to ensure it's right. Because, 30, we know that it goes in the beginning, but the algorithm doesn't know that. So it literally needs to compare against every other value. That's why it takes so long.
Okay.
Yeah. Okay, and then let's check out some code. That mostly makes sense?
Yes.
Okay, so can you think of a little bit of how this code would look?
Would it also be a nested for loop?
Yep, you're exactly right. It would be a nested for loop. Can you tell me why?
Pretty much the same reason as the others. After it goes through one value, it has to check all of the other values, but it needs a for loop that's kind of remembering where it is and checking all of the values and sorting it in the right order.
Okay, cool. Yeah, that's exactly right. So same thing with like, same kind of logic, like selection sort, where like you start at something, right? And then you want to do this procedure for every single element, and then the procedure itself involves you going through everything, you know. So that's why it involves you going through multiple things. So that's why you need the sorting algorithm, right? That's why you need the second loop. Yeah, and in this case, they like using a while loop, but I think you can use a for loop if you want. It's up to you. I think the reason they use a while loop is because they don't know. Yeah, it's because they don't know like when exactly that value. Like when you're comparing back after when you're comparing the new value to the already sorted list, you don't know what exact spot it's gonna go or how many times it's gonna have to move. So I think that's just why they use a while loop. But you can do whatever you want. It doesn't need to be that. So can you kind of tell what's going on in this code? Like if like walk me through like each line.
So
Like
first you have to.
starting at like line 7. Like I
Okay.
know what a public static void is in the context
Okay.
of this question.
So first you have a for loop that is going to be going through all the elements until the last element.
Right, that's exactly right.
It sets this temporary integer that will hold on to whatever element it's currently on.
Mm-hmm.
And then it also has another temporary integer that is keeping track of whichever is the lowest value to be set to the first value in the new array.
Mm-hmm. That's exactly right.
And then within the while loop, it's basically checking to make sure that the integer temp is smaller than the possible index. If not, then integer temp will become the possible index.
Mm-hmm. Mm-hmm.
And then it's going to keep going until it's in numerical order, ascending.
Yeah, yeah. So you can see here is like kind of when we're doing this thing where it moves like it moves it like one by one as opposed to moving it, you know, a bunch of them a bunch of times.
Right.
Yeah. Cool. All right. And okay. Yeah, I think that's pretty much it. Yeah, it's just like same with selection sort. It's just remember you're gonna have 2 while loops, and you can see here some of the traits to identify uh, when you're using insertion sort. I think you mentioned most of them. Yeah, auto loop that starts at 1, loops an entire array. You said that. So the element value at the outer loop. Yeah. Yeah. So you made note of all the things, but yeah, if you need like a cheat sheet of how to tell how any of the algorithms look, this is a all the lessons in the book have one of those.
Okay.
Yeah. So yeah, same. You can see, yeah, like I said, same questions as the other one. They really want you to think when an algorithm performs well, when it performs bad, and I think we talked about this, right? So you can tell when is it going to perform the best,
When it's already in the ascending order.
right? Yeah, exactly. Because it's already in order, so it doesn't need to move anything. It'll look through everything, but it won't move anything. So it doesn't take that long. And it doesn't do as many compares as the other
Right.
one. Yeah, it's a key word there, comparing. And then yeah, and then what's the question here? But it does not work. Okay. Think you can work through this one?
Because
I'm sorry?
the entire length.
I can't quite hear you. Looks like your voice is cutting up.
Sorry, can you hear me now?
Yeah, that's good.
Okay. I think that it's line 1 because it needs to go through every element, but this will leave off the last one.
It'll leave off the last one? Okay.
Yes, with line 1.
Okay. Let's try that. Yep. But I think, yeah. What? So, do you think the problem is here? Is that what you think the problem was? I didn't quite understand that.
Yes, the problem was there.
All right. I think the actual problem is actually no. Yeah, you're right. Yeah, the problem is there. Yeah, you do need to go through the entire array, right? I thought the problem
Or
was here.
doesn't, yeah, J equals 11, I mean 0.
Yeah, I think it actually is here. Actually, yeah, I think you should be starting at 0, and then yeah, you know that this one is already sorted, right?
Mm-hmm.
Yeah. So I think the reason why that happened is that
Or could it be both?
I think it could be 0, but they accounted for it being 1 here. They have this check here, so they don't accidentally move the 0 element where it doesn't need to be. But I think if they didn't have this possible index greater than 0, then you would need to start at or this possible check, then you would need to start at 0. I think that's why they did. Yeah,
Okay,
I think that's why they did that. But yeah, also this part. You
right,
basically you just know you want to go through the entire array.
right.
Okay, and then I'll talk really briefly about merge sort. Like I said, it has recursion in it, and I know you don't know that as of now, but I'll just talk kind of briefly about how it works. And then once you learn recursion, you can ask in the group me or private message me or anything, and I can help you learn that if you need any help.
Okay.
Yep. So merge sort is actually a lot faster than the other ones, and maybe you'll be able to tell later. But it's basically got three different parts, right? It's got the merge sort part, the merge sort helper part, and the merge part, right? And for this one, actually, I think I really like the Wikipedia. Wikipedia has a little GIF that shows merge sort, and I think that's probably the best one I've seen, or at least the most straightforward one, right? So, what is it? So yeah, are you seeing this little GIF right here?
Yes.
Yeah. So basically, what happens in merge sort is that you want to break up the array into different chunks. You want to sort those
Mm-hmm.
chunks, and then you want to merge those chunks that are already sorted. So let's restart this kid. So you can see it starts out. Oh, it doesn't. That's the only bad part about GIFs. You can't like reset it, right? So initially,
Mm-hmm.
what you want to do is that you want to break it into the smallest size components you can think of, right? And so the
Right.
small size you can think of is elements of 1. That's why at the beginning of the array, everything was broken up into little pieces of 1. And then once
Yes.
you broke it, once you break it up into those little pieces, you want to compare the neighbors, right?
Right.
Yeah. So in this case, 1 and 3 are neighbors. You compare those two, and then it becomes 1 and 3, a little subarray, right? And then you
Mm-hmm.
compare 5 and 6, or whatever was the second element, and you want to make sure those two will be sorted. And now and you keep doing that for every pair, and at the end you'll have 4 subarrays of 2 elements, right? And
Right.
but those are already sorted, right?
Right.
Let's just say it happened, right? Yeah. So see, the initial part is breaking everything up together, and this is when the recursion happens. You'll learn a little bit more about recursion, but basically you want to break it up, and then you want to kind of work back from where you broke it up, but place it in the correct spot, right? That's how recursion works. That's how recursion kind of affects this, and you'll notice that when you learn about recursion, it'll make a lot more sense. But yeah, so you sort it into 4 different subarrays, right? And then again, you want to compare the neighbors, right? So you compare 5 and 6 and 1 and 3, and then you create an array of 4 elements, and you do the same with the next one.
So is this faster than selection and insertion sort?
Yes, it's faster because so you know how those guys had to go through the entire array multiple times in many
Right.
cases, right? So this one doesn't need to go to the entire array. You're going through little arrays every single time. So instead of searching through eight things every single time, or possibly searching for 8 things every single time, you're searching for only 2 things every time, or only 4 things every time, or only 6 things, and then you only search for 8 things once at the end. So it's a lot faster because you search through less things. and you're guaranteed to do that. Whereas in the other ones, you had bad chances of that. However, yeah. However, can you tell a possible bad thing about this algorithm? It might not be that obvious, so it's okay if you don't get it.
What if, would there be a problem if there's duplicate numbers?
Duplicate numbers?
Yes.
That's a good point you bring up. But I think in general, you'll notice that with sorting, duplicates don't really have that bad effect on it, because when you have duplicates, the only thing that means is that, oh, I can put these duplicates, this one first or this one first. It doesn't matter because they're the same thing. So you'll notice that in sorting, duplicates don't really have any effect on it, or like they won't hinder the algorithm's performance.
Okay.
But that was a good suggestion. That was a good suggestion, though. But yeah, the problem that this will have is that, so remember how like you're breaking the array into little arrays, right?
Right.
Yeah. So what that happens means is that you're occupying more space because you're having little arrays, right? Instead of having one array, you have a ton of arrays, right? And this isn't a big deal in this case because you're only making 8 little arrays. But imagine the list was 1,000 things. You're gonna end up with 1,000 little arrays, and that's 1,000 different like variables and arrays that you need to create for that. 1,000 different spaces in memory that you need to create for that, as opposed to just one space in memory for that entire array, right?
Right.
So if you don't have a whole lot of space to work with, this isn't a good algorithm because you need to create all those little arrays. And that's another thing to consider. As you'll notice, like in the Big O cheat sheet, they also talk about space complexity. That's what that's called, right? And so you'll notice that the merge sort, the space complexity for merge sort is not that great, even though it's a lot better in time complexity. You can see this one is yellow, and a lot of the other ones are of 1, which is the smallest. So yeah, like I said, don't worry too much about Big O because I don't think it'll be in their test. But just worry about, like, if you're ever wondering, like, oh, which one's faster, which one takes up more space, just look at the colors and that'll tell you like what's better, And you can see here, like, how good each of them are, depending on how many operations are done and how many things are in the array. So yeah, this is just a little cheat sheet if you ever want that little breakdown on that.
Okay.
Right. Yeah. And so I think so you got the general picture of merge sort, right?
Yes.
Great. Yeah. So that was a big overall problem of like how it works, but it's broken down to these 3 different steps, right? Merge sort helper, and then the actual merge, right?
Mm-hmm.
So without like looking at the code, can you tell me how each of these would be like used in the context of like the actual algorithm that we just talked about?
So merge sort would be called with, do they take any parameters?
Yeah, they take in some parameters. Let's say that let's
so
say
it'll take in the array?
Yeah, taking the array. That's exactly right.
So merge sort would be called with the parameter of the array, and then merge sort.
So yeah, so let's think about this in the order of like the array, right? So you first you give the algorithm the array, right? And now what do you want to do that you have your array?
Right.
You want to break it down, right? Break it down to those little pieces. So that's what merge sort helper does. It'll break down the array into those little pieces, and then this was probably pretty, yeah. And then I'm sure merge is kind of intuitive, but what do you think merge does after you break it down into little pieces?
It puts the pieces together.
Yep, exactly. So you'll see the recursion here. I really don't want to talk about recursion because I don't want to confuse you more. But just know that recursion, what it'll do is that as you break it down, like think about it like you're breaking it down, right? And then you get like like the smallest step, and then as you piece it back together, it's like you're going up a ladder and then coming back down, the same ladder, but you're changing like your clothes or something as you're doing that. That's kind of like the way I think about it. You're still in the
Okay.
same ladder, you're still doing the same process, but you're changing things as you're doing that process.
Okay.
Yeah. Um, yeah, I guess you should be able to ask these questions. Oh, we already talked about this one, but just to make sure, which one of these is the fastest? Or
Is
which second question?
the second question?
Yeah.
Is the fastest?
Yep. And do you
Not sure.
remember why? Kind of.
Um, because it kind of works in pieces, so it doesn't have to run through each item in the array several times. It just runs through smaller arrays and then pieces the smaller arrays together.
Exactly. So instead of searching like, oh, for this one element, I'm going to sort it based on like this entire list. So I need to look through the whole thing. I just look through the small little subarray, right? And then those are already sorted, which make the job easier later on. So yeah, it's a lot better than selection sort and insertion sort for sure. And oh yeah, and can you think of any case in which merge sort would perform faster?
Um,
Or like when does it perform fastest?
take the same amount of time to execute because it would still put them in the groups.
Yep, you're exactly right. It's always going to break down everything into those smaller groups. So even if the smaller groups are already sorted, that just means that you won't have to switch things around as much. But it'll still continue doing the breaking it down and the comparing. So you still, as long as the comparing is still the same, which it is still the same, then it'll take about the same amount of time. So that's why it takes about the same amount of time.
Okay.
And that's it. That's all you need to know. Well, besides the merge, the recursion part of merge, that's all you need to know about searching and sorting for the AP test. It's not a whole lot. I think it'll just be a couple of conceptual questions from what they told us. But yeah, do you think you feel a little bit better on those subjects now?
Yes.
Okay, great. So this weekend, if you're not busy on Sunday, we're doing in-person session where we'll actually like work through some examples on the board and have you guys code, and we can like give you feedback on the code and see what you did wrong, or like help you out with anything you need. Maybe like if you have some homework you'd like us to look at, and like or anything you have questions on, and if you want some free pizza and free swag, we're doing that. So I think Barb posted the link in the group me. So
Yes.
did you see it?
Yes, I signed up for it. I will be there.
Great. That's awesome. Well, I guess we'll see you then. I'll be there with a couple of the other people from Project Rise Up, and hope this has been helpful then.
Okay. Well, thank you so much.
No problem.
I will see you.
Yep. Look forward to meeting you on Sunday.
Bye.
See ya.